When we consider a microscopic view of gases and compare them to a liquid, we can really see a few things jumping right out at us. So we can see that the liquid is going to be much more closely spaced. Gases are going to have lots of space in between them. And I do want to point out that, yes, here I'm showing them moving back and forth in a straight, repeatable line, and they're not colliding with each other. That's a limitation of my animation skills in PowerPoint. That has nothing to do with the physical phenomenon. These things are actually going to be zipping around as far as they can go, bang, 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 all the way across. They're going to ricochet off of something. It's going to be a completely elastic collision. They conserve their total amount of energy. There's no sticking or repulsion that happens. And liquids would also be moving in a chaotic fashion instead of this straight back and forth line as well. Limitation of my artistic skills. Now, the gas phase molecules have a lot more space in between them, and they have a lot more kinetic energy that you see up in this region. Now, some implications of that, and these are really important. This is going to make the gas far more compressible than a liquid. If we start pressing down on a liquid, it's going to be something where we can barely compress it at all. That's actually how hydraulics work. They can transmit a lot of power because the liquid itself isn't going to compress significantly as you press down on it. Gases, however, definitely compress. And if you've ever grabbed one of those little plastic syringes that you give a cat medicine or a child medicine with, you've held your finger over the tip, and you've pressed down on it with air, you've been able to feel how much you can compress it with air. When it's water, it's almost like you're pressing on a rock. It doesn't move much at all. So liquids, not very compressible. Gases, you can definitely decrease the volume and increase the pressure in the process. Now, thermal expansion. Liquids don't change their density dramatically when they heat up. Gases really do. Also, the viscosities are dramatically different. If I'm walking through water, it's a very viscous sort of thing. If I'm moving through a gas, it's not very viscous at all, and I can move through very easily. Also, look at the difference in densities. For liquid nitrogen, we're at a density of 0.8 grams per milliliter. When it's a gas, it's 1.25 grams per liter. Notice the difference of 1,000 in the unit prefix. So while the value is comparable, it's an order of 1,000 difference. So that's going to be a dramatic difference in densities. Also, they are going to be miscible. So if you have liquids, even if they would have separated out like oil and water, if you heat them up enough that the oil molecules are a gas and the water molecules are a gas, they are going to completely mix together in a totally uniform fashion. That's what miscible is going to mean for us. So those are some of our key properties when we look at the microscopic view of gases and connect to some of our macroscopic phenomena.